All right. Unit 3, Day 2, September 5th, Tuesday, derivatives of log functions. But before we get to derivatives of log functions, we're talking about log functions before derivatives. And even before we get to the properties, let's just back up and make sure we remember what a log means. Like log base A of B equals C. How could you rewrite that as an exponent? Do you remember the loop-de-loop fishhook thingy? A to the C equals B. A to the C equals B. Fishhook, start at the base, loop around. A to the C equals B. That's what it means to be a log. It's just undoing, it's an inverse of an exponent. Okay, again, we'll do some review first here. These are called transcendental functions as opposed to algebraic functions. You don't need to know that. But you do need to know the log properties. How about natural log? What is that missing base that's right there? Well, for natural log, it's base E. For just log, it's base 10. So natural log of x is the same thing as log base E of x. And you'll never see this written because we have a better way to write it. But you need to know that natural log means there's a base of E. Now, natural log of E equals something. Let's think about the loop-de-loop thing. Hopefully you have those memorized, or you will soon. But if you got to think about what the fishhook thing is, that means E to something equals E. So what's the something? What goes in the box? E to what power would give me E? 1. Natural log of 1. That means E to something gives me 1. Well, E to what power would give me 1? 0. So natural log of E is 1, natural log of 1 is 0. You need to know those because those are going to come up a lot and it'll make your life easy if you know them. Let's hop back up here. Natural log of x times y. Do you remember how to split that up? Like there's a property that you can use. Natural log of x plus natural log of y. Well, hopefully it makes sense that if multiplication leads to addition, then division leads to subtraction. And if there's a coefficient out front, it can go up top as the exponent. So the natural log of x to the a. And just a reminder, these are not the properties over here. You can't distribute a natural log. It doesn't work that way. But these have parallels, and that's why it gets confusing. So natural log of x times y, you can split up into natural log of x plus natural log of y, but it doesn't work this way. So be careful. This is the mistake area over here. By the way, this is the calculus is easy, algebra is hard section, which is why we're reviewing the algebra. None of this is calculus. This is all algebra. You saw it in Algebra 2. You saw it in pre-cal. You're seeing it again. From this moment on, we're going to sort of assume that you know how to do this, because now we're going to, in a moment anyway, transition to the calculus part. Domain. Let's hold off on the domain. Do you remember what the graph of it looks like? Well, we already have 2 points. We didn't have 0. We couldn't plug in 0. We could plug in 1 and get E. Wait, that's backwards. The natural log of E is 1, and the natural log of 1 is 0. there's 1, 0. E is like 2.7. So 1, 2.7, comma 1. And the graph looks something like that. And again, it's helpful to know that because there'll be times where if you can picture the graph, you can answer the questions easier than using a formula. Okay, so looking at that picture, what's the domain of natural log of x? What x values are covered? 0 to infinity, and don't include 0. You can't take the log of 0. Another way to say that, exact same thing, would just be x is greater than 0. Okay, some limits. All right, looking at my picture, let's answer these limits. We'll go Mia on the first one and Lauren on the second one here. So Mia, as x gets closer to 0 from the right, right? 0 plus means 0 from the right. So as x gets closer to 0 from the right, so like 0.1, 0.001, 0.00001, what is my graph doing? Where's it headed? As x gets closer and closer to 0. It's decreasing, so where is it headed? What's the answer to this limit question? Good, negative infinity. Lauren, on the other end, as x gets bigger and bigger, so way, 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 way out there, what is the graph doing? It's going to infinity. Now, we don't ever really differentiate here, but it is okay to think that it's going to infinity like slowly, right? There's some graphs that like shoot way up. This one it's always increasing, but just barely so. So the answer is still infinity. It's just a lot slower to get there than like a parabola would be, or even a line would be. So yes, the answer is infinity, but it's getting there slowly. Let's see, natural log of x has a vertical asymptote of, I could call on somebody for that. Tyler, you see any vertical asymptotes in this problem? Yes. And where are they?
X equals 0.
Very nice. X equals 0 would be my vertical asymptote. Okay, so all of that is like background algebra review stuff. Like that stuff. I mean, I don't expect you to have known that right off the top of your head walking in this morning, because natural log's not easy. But hopefully, after we went through it, hopefully it was all familiar. You're like, yeah, I remember now the properties and natural log of e, natural log of 1, roughly what the graph looks like. Limits are new, but if you got the graph, it's not hard to get the limits. Okay. In past lessons, we've sort of skipped the exploratory part, but it's helpful to know how to do it, and I think this is one that we could actually do. So grab a calculator. You can go grab one of mine if you need it, or get your own out. Go to y equals and plug in y equals natural log of x. So this isn't new. We know what this graph should look like, but this will at least make sure we're kind of on the right page here. So y equals natural log of x. Let's go to Zoom. I would say Zoom Standard to start with. See what that looks like. Why don't I see anything? Oh, because if you highlight the equal sign and press enter, it turns it on or off. And so you can have multiple graphs in there and not watch them all at the same time. My natural log x graph was turned off. Ln is on the left-hand column there toward the bottom, third from the bottom. Let's see. It's so steep it runs into that runs into the axis, so it doesn't look like it goes all the way down. I wonder if we went to zoom 4, if that would look any better. Maybe not, I don't know. I went to zoom 4 to put it into z decimal. That means that your graph isn't distorted. That's the aspect ratio is correct if you do zoom 4. Okay, that we knew. That we just looked at. What I want to do now is figure out how to basically sort of trick the calculator into graphing the derivative without me knowing the derivative. So this is going to be kind of wild. We haven't done this before. So go back to y equals, and I want the derivative of that. So the calculator can do derivatives. Press math, and you scroll down, and one of the options, option 8, is in derivative. Press that. And if you've got a newer calculator, it looks nice. If you have an older calculator, it says in derivative. And you can still do it, but you have to know the right format and notation to make it work. So if you've got one of these calculators, I would get a different one, because you don't want to mess with that. Okay, so I want d dx of natural log of x. Oops, it needs another parenthesis there. So that means take the derivative of the natural log of x and evaluate it, right? That bar means evaluate it. If I put a number in there, like if I put in at x equals 1, it's just going to be one number. But I don't want it to be one number. I want it to evaluate it at all the different values of x. So this is kind of a labor-intensive process for the calculator to do. I'm turning off the first one so I only graph the second one, because the calculator doesn't know derivatives. It knows the definition of a derivative, so it like manually calculates a slope at each spot. And so for each little dot, it has to calculate a slope. And this one's not too bad, so it graphs it relatively quickly. Compared to some, but you can see it's a little bit slower because your calculator is calculating every single spot what the slope is. Does that graph look familiar? Does it look like a graph you're familiar with? It's a parent function graph you should be familiar with, so that should narrow it down. Go to table then. Second table. See if that confirms what you were thinking is. X is 1, the derivative is 1. If x is 2, the derivative is 1/2. If x is 3, the derivative is 1/3. Although you can look out there at the end. This is because the calculator does things numerically. So when you're out 7 or 8 decimal places, it kind of loses track of what's going on. So it's 1 over x, 1 over 4, 1 over 5, 1 over 6. You're not as familiar with the rest of them, thank you. 1 over 10, you know. So yeah, it's 1 over x. So that means the derivative of the natural log, let's skip all that, the derivative of the natural log is 1 over x. Now, the derivative of the natural log of u, so if it isn't just x, then it's a chain rule situation. So it's the same rule, 1 over u, but then the chain rule says times u prime. And a lot of our problems today are going to be chain rule, because if they weren't, every single answer would be 1 over x. So we make this argument of the log a bunch of different things to force us into the chain rule. All right, well, if our base, all of that was for base e. So let's fill those in. So the first one we know, 1 over x. And 1 over u times u prime, chain rule. This property of log, you may not know. Log base b of x is the same thing as natural log of x over natural log of b. So that if we take that derivative, natural log of b is just some number, who knows what it is, but so 1 over natural log b times 1 over x. And then, oops, that's the same thing. That should probably be a u right there. So 1 over natural log b, 1 over u, u prime, chain rule. So there's our new rule. I would say it's one rule, although I guess it kind of looks like 4 rules right there. That's the new rule for the day, the derivative of the natural log. 1 over the argument times the derivative of the argument. In words, derivative of natural log. Some people are more word people. 1 over the argument times the derivative of the argument. Again, it's math, so you should probably be memorizing formulas, but if you need it in words, 1 over the argument times the derivative of the argument. All right, let's do some examples. Find the instantaneous rate of change. Well, that just means derivative. Again, we're just going to keep using all the different words to make sure you don't forget any of them. At the point when x equals 2. Okay, so dy dx, 1 over the argument, so 1 over 3x squared minus 4x minus 1. But then chain rule times the derivative of the argument. So, Nick, what's the derivative of 3x squared minus 4x minus 1?
6x minus 4.
Good. So, tons of little built-in review today. And we're not done because it said when x equals 2. So that means I need to evaluate that at x equals 2. So 6 times 2 minus 4 over 3 times 4 minus 8 minus 1. Right, doing a little bit of evaluation as I plug in there. That's a safe stop, so that would be fine on a free response answer. 12 minus 4 is 8. 12 minus 8 is 4. Minus 1 is 3. 8/3. And again, safe stop versus multiple choice. And even on a multiple choice question, you would be wise to show your work, label your work, so that if you mess something up somewhere, I can figure out if it was an algebra problem, so you'd only lose a few points, or if you really didn't know what you're doing, and then you'd lose all of them. But at least give me a chance to give you some partial credit. Number 2. If g equals that ugly thing, find the slope of the line tangent to the graph. So again, that's just derivative. Slope of the tangent line. Alright, well already I see a root. I don't like roots. I'd much rather powers. So a cube root. Alan, how could I rewrite the cube root as a power? Yeah, so I'm going to rewrite that as 1/3. That way I don't have the cube root anymore. I'd much rather deal with powers. And then one of the properties of logs that will make this derivative a lot easier than it's going to be, like I can take it here. It would be 1 over all of this times the derivative of all that, which would be really yucky. But there's a property that says I can take that 1/3 and move it to the front. So 1/3 natural log x cubed minus 3x. And now this is going to be much easier. So g prime, because now that 1/3 is just kind of going along for the ride here. 1 over the argument, x cubed minus 3x. What else do I need to include in this answer, Quinn? You stepped out for a few minutes. 1 over the argument times the derivative of the argument.
The derivative of the argument.
Which is?
3x minus
3x
squared minus 3.
Yes. So chain rule is sort of built into every natural log problem. 1 over the argument times the derivative of the argument. And that's a perfectly good answer. But let's see. It's a little bit cleaner just to write it like that. And the 1/3 could reduce, the 3's could reduce. So multiple choice answer would probably sort of fix that 3 business. And it would look like that. Again, be neat, show your work, show your steps. And if you make a final mistake from here to there, that's just a couple points off. Unless I don't see anything, and then it's all the points off. So the big lesson from that one was do the algebra first if you can. Do the algebra first if you can, because it makes the derivative a whole lot easier. Yes, sir.
Could you go back to the written portion of the rules?
Like when I spelled it out?
Yeah.
The derivative of the natural log is 1 over the argument times the derivative of the argument. And so that, again, that's how some people remember it. That's how I remember it. I know the formula, but 1 over the argument times the derivative of the argument. And that times derivative of the argument, that's the chain rule showing up. Number 3. H of x equals that thing. Okay, I could take a derivative now. It would be 1 over this thing times the derivative of that thing. What would I have to use to get the derivative of this thing? Quotient rule. So I would have a mess on my hands, right? I'd have 1 over a fraction, so that would take some cleanup. And then I have the quotient rule, which would be a mess. So let's do algebra first. So let's see, that would be natural log of 2x minus natural log of x plus 3. That's going to be way, way, way easier. So Brandon, what's the derivative of the natural log of 2x? Walk me through it. I'm not expecting you to give me the final answer right away. How do I find the derivative of a natural log? Think about the words we used earlier. 1 over the argument times the derivative of the argument. So 1 over, yep. And then the derivative of the argument would be 2. And so it turns out to just be 1 over x. Minus, Grenier, how about the derivative of natural log of x plus 3? Pardon?
1, like 1 over x.
What's the argument? What are we taking the natural log of? It's got to be that whole thing. So 1 over x plus 3. And then What's the derivative of x plus 3?
X. I mean 1.
Just 1. Perfectly good safe stop, but we look at our answer choices and none of those match up. So how do you think we get from here to here? How do we combine fractions?
Common factor.
Yeah, get a common denominator. So that would be x plus 3 minus x all over x times x plus 3. In the top, the x's cancel. So 3 over x times x plus 3. Sure hope that's one of my answer choices. And it is. Number 4. dy dx if y equals natural log of the secant of x. Well, okay. That would be a weird graph to think about. But, you know the rule. So, Rabia, what's the derivative of the natural log of the secant of x? Yep. Good. Perfect. So, weird problem, but you know the rule. So, apply the rule. 1 over the argument times the derivative of the argument. And then, again, my answer choices don't look exactly like that, but the secant can cancel. And so it turns out to just be tangent of x. Which is kind of weird that you, pretty rare that you start out with something weird, take a derivative and get something easier. Usually things get more complicated rather than getting easier. Okay, let's see. Starting to get short on time. 5 has a different base in there, so let's handle that. But the different base just means there's a natural log 7 out front. After that, it's all the same. So a different base, again, just puts natural log of the base in the denominator, and then the problem is the same from there. So 1 over 3x to the 5th times 15x to the 4th. That's a perfectly good safe stop. There's obviously lots of cleanup work that could be done, but let's say that we're done with that one. What would you need for the next one? What rule would you need for that? (3x log base 5 of x squared plus 7). What's going on there? The product rule. So let's see. The first times the derivative of the second. So the derivative of that one, well, there's that 5 in there, but that's easy enough. 1 over natural log 5. 1 over x squared plus 7 times 2x. So chain rule within the product rule. Back up, I'm still thinking product rule plus the other way around. Although the other way around should be easy. Derivative of the first one's 3, and then just leave log base 5 of x squared plus 7. Now, who knows what they do in terms of cleanup for a multiple choice answer, but that would be a good safe stop. Number 7, it looks terrible, and if you tried to do it as is, it would be terrible, but it'd be a whole lot easier if you just split it up into natural log of x plus 1/2 natural log x squared minus 3 minus natural log of cosine of x. Alright, use the log properties. So rather than having to do this awful looking thing, now you've got 3 relatively easy problems. Oop, made a little mistake here. I should have labeled that. So when I switch to prime, when I switch to derivative, let's see, cosine in the bottom. What's the derivative of cosine? Negative sign. And then there's some cleanup work, like that might be written as a tangent in a multiple choice problem. And then that last one, kind of the same deal. If you'll rewrite it using algebra first, it'll be a lot easier, a whole lot easier. And that'll be using the graph. All right, worksheet 2. Again, the best way to do a calculus class is to do the homework, all of it, the day it's assigned. That way you come in tomorrow and you know where you have issues, or maybe you don't have issues, but at least you'll know you're good. So, strong encouragement that you work on the homework tonight. Don't save it all. Work on it tonight and come in with questions tomorrow.